So I'll type it, go 2 or 3 questions, to receive it by tomorrow. So last time we were, I hope we are now 32. I think that's a good number. So we can start. I hope you have had a good week. Today being Thursday and you're enjoying yourselves. So we are still looking at the opioids, also known as the narcotic analgesics and analogs. Then we have looked at the structural modification of morphine. So far, we've looked at the periphery modification. We've looked at the 3-methyl group. We've said it must be there. It must be a free hydroxyl group for optimal activity. Once you change it, like you change it to a methoxy group, as in codeine, you change activity, you lower the analgesic activity, you introduce antitussive activity. Then we looked at position number 6. We said it is not necessary to be there for activity. You can remove it completely with increase in analgesic activity. You can oxidize it to a ketone with increase in activity. You can also acetylate it, like in monoacetyl morphine, and with increase in activity. And we discussed all this. So we'll continue with the same. But before we move on to the next structural modification, we discussed all the structural modifications, even how you can change the nitrogen. We discussed how can you change the nitrogen, the substituent on the nitrogen. We said methyl is optimal, ethyl is acceptable, anything between 3 and 5 brings about a narcotic analgesic activity, antagonist activity, brings about antagonist activity. We explained that once you make it between 3 and 5 carbon atoms, you bring about steric hydrants, and therefore the molecule is not able to interact with the receptor. So we discussed all that, but I did not explain the reason why. When we change, we also discussed the group 7-8 double bond, its saturation and oxidation of the 6-hydroxyl group and what it does. We only mentioned about changing the conformation of the ring C from boat to chair. But before we move on, I want us to discuss and understand what happens when we change the hydroxyl group at position number 6 to a ketone and also do saturation, because it all is about changing the binding, shifting the group a little bit, shifting removing the hydroxyl group. The hydroxyl group is very highly polar compared to the carbonic group. Carbonic group has a slightly higher lipid solubility than the hydroxyl group, and it's just about the binding with the receptor. So I want us, before we move on to any other structural modification, I explain why changing the changing we had talked about, why does it bring about increase in activity. So we are saying, we had mentioned this, I'm just going to that, we should have discussed it last time, but unfortunately, I think I've forgotten this slide. Replacing the hydroxyl with a methyl or methylene increases mu receptor affinity. I said, when you look at the structure of naumifene is a pure antagonist. You can see, if you look at that structure here, this is naumifene. Naumifene, this is the methylene group. If you look at naumifene, but naumifene, because of the group which is at position number 17, it's an antagonist. But if this was a methyl group, if this was a methyl group, and this was a methylene group, that compound will have very high agonist activity. But of course, the minute we put this to be a cyclopropyl methyl group, that is too large and it introduces antagonist activity. That is something we had already discussed. I hope we can indeed remember that. So we are saying when you introduce this group there, you increase the mu receptor affinity, again, due to better hydrophobic interactions. So when you remove the hydroxyl group, you can see already you have also removed the double bond, and you have now the chair conformer, rather than the boat conformer. So this group has shifted a little bit, and it's giving us very, very good hydrophobic interaction. Example, you have naumifene, introduction of additional, so naumifene, but of course I have explained that naumifene is not an agonist, but nevertheless, when you introduce this group there, it binds the receptor more more strongly. But because of this group, that is what changes it to be an antagonist. But the whole of this other portion makes that compound bind very strongly. So introduction of an additional hydroxyl group at carbon 14 increases again mu receptor affinity due to an increased hydrogen bonding to an allosteric site. That I remember we had already discussed. That when you put a beta hydroxyl group, remember, at position number 14, these compounds increase in their binding to an allosteric site within the mu receptor or the opioid receptor, because hydroxyl groups can bind with other areas through hydrogen bonds. You know that oxygen bond bound to a hydrogen can bind with another center and so on. So it can interact with the receptor site within the receptor, and therefore bind this molecule more strongly. And when the molecule is bound, it gives the molecule higher affinity. It binds more strongly, and therefore that improves on its potency. The carbon 7, carbon 8, double bond or olefinic bond saturation changes the lipid water partition coefficient once you do very slightly. And indeed, with this saturation increases the activity, analgesic activity slightly, and mu receptor affinity. So it increases both the mu receptor affinity, and also it increases the lipid water partition coefficient or lipophilicity. The molecule penetrates the membranes more rapidly, both the lipid membranes within the GIT and the membranes within the brain, and therefore you get higher concentration. Of course, we have better activity. Saturation gives a slight increase in lipid water partition coefficient, and also ring C goes from boat to chair conformation. That is what you see. This is a boat conformation there. That is a chair conformation. The chair conformation is once you do saturation. That changes the 3D position of the 6-hydroxyl group. This gets rid of the unfavorable hydrophobic hydrophilic interactions. If you look at this molecule here, you look at this, this is now, you look at this molecule, this is our morphine. No, this is our, it has the double bond there. So this is not dihydro, this is morphones. This is morphone. This is morphone. This is our structure, morphone. It has the double bond and it has the ketone there. So when you look at that compound, you can see this is supposed to be our hydrophilic center. So you can see once you have not changed the bond conformation. Remember we said when you just make it a ketone and you do not change, you do not saturate, indeed there was almost a decrease in activity. And you can see there that because without changing the conformation of this ring C, this is the hydrophilic center, this is the hydrophobic center. There is too minimal interaction between the hydrophobic center, and that is what we want to get rid of. Now look at this. What have we done here? We have changed, we have saturated that bond. We have changed from bond conformer to chair conformer. And can you see what happens? That the hydroxyl group, because this is now the dihydromorphine, the hydroxyl group has shifted completely. That is the lipophilic center. It has shifted completely, and you can see it's in the middle here. So we have now removed the unfavorable hydrophobic, and the hydroxyl group can go to its own area where it can interact with the hydrophilic areas and therefore give us better activity. And that is why we did mention that hydromorphine has much higher activity compared to morphine, because that's all we have done there. And by just saturation, although that remains as a hydroxyl group, change of the conformation changes the position of the hydroxyl group, removes the unfavorable hydrophilic, hydrophobic interactions, and gives us better activity. Now look at this next. This is, as you can see here, we are considering this to be a polar site. This is to be a lipophilic site. Now when we do saturation, the group even moves further. So this is on saturation. I'm sorry, on oxidation. Sorry, this is on oxidation. When we do oxidation now of the hydroxyl group, you can see now the ketone moves even further and interacts with the polar site. So that gives us very good hydrophilic interaction. It moves away from the lipophilic center, it moves away from the center, and just by oxidation, indeed, when we oxidize that, then that now gives us, in the dihydromophone, it now gives us the interaction we want, hydrophilic interaction, and therefore that compound has much more activity. Now, when we look at now-methane, of course, when we do this now, you can see this is the same change. So instead of the ketone here, put, so that is when we do the ketone, that is when we do the ketone there. So when we do for the now-methane, as we said, what happens is that is a boat conformation. This somehow interacts with, has better interaction with the hydrophobic area. So we are therefore saying changing or doing the structure modification is only altering how these compounds are binding to the adjacent or to the allosteric site. Because within the main receptor, you're going to look at the main receptor. There are other areas, the allosteric sites, where you can have a deficiency of electrons, an excess of electrons. When you have an excess of electrons, it can be negatively charged, so it can be hydrophilic. So, and within the receptor, you will get such centers. You will also get molecules that are charged, or that have carried charge. And therefore, this when you do structure modification of this morphine, then you are able to interfere with the way the molecule is interacting with the allosteric site, and therefore giving more activity. So that's just what we're saying, that this gets rid of the unfavorable hydrophobic interaction, that this also increases this also increases U receptor affinity. Saturation plus oxidation of the carbon-6 oxygen produces an increase in the mu receptor affinity, as we have seen. The ketone is more rigid and held away from the hydrophobic region, may even interact with an adjacent hydrophilic region. So I think that's what I wanted to explain, that is what explains why the structural modification at position number 6 and position number 7, 8 has an overall effect on the activity of this compounds. I hope that is clear. So that I hadn't explained. This we had looked at last time. I remember we had gone up to slide 57. Is only that I had not explained that. So I was coming now to this summary. We had mentioned, again, kindly remember we said position number 17 is very, very important for potency and also the type of activity. Is it going to be agonist activity? Is it going to be mixed agonist, antagonist activity? Is it going to be a pure agonist? All that is dependent on what you put at position number 17 on the terminal nitrogen. What you put in these other positions, whether you put a hydroxyl group at position number 14, or you change the group at position number 6 to be a ketone or a methylene group, all that does is helping that molecule bind the receptor more strongly. So if you have an antagonist and it has those groups in position number 6, in position number 14, it will bind the receptor very strongly. And now, so it will bind the receptor strongly, but because of steric hindrance, so the way it binds to the receptor, it is binding there strongly in the surrounding area. But the important area where the terminal nitrogen must bind, it is not able to bind because of steric hindrance, and that terminal nitrogen binding the receptor is very important. It's not able to bind because of steric hindrance, although it is binding the exterior portions of, or the other parts of the receptor. There is an area which is actually the anionic center. It's not able to bind it because of the steric hindrance, and therefore that molecule will have antagonistic activity. So therefore, when you see the antagonists carrying the same groups carried in the agonists, is to help secure or anchor that molecule within the receptor. But because of that specific group, which is larger than it's supposed to be, it will introduce an antagonist activity, as we had already mentioned. So that is why those groups are repeated. Summarizing the effects of altering chain length or nitrogen or morphine, this is just summarizing. If R is a methyl group, like in morphine, you have best agonist activity. We did mention the ethyl group is acceptable, but as you continue increasing that group, agonist activity decreases, antagonist activity increases, as we had said. When you change that group to four carbon atoms, like in butyl group, there is no activity. Then now here, it is actually the same, that you have CH2, 1, 2, 3, 4. This is even bigger. Those are 5 carbon atoms. Then agonist activity increases. Remember, we did mention again, beyond 5 groups. You see, we said up to 5, but you can see this is, we said 5 to 10. That is 4, 5, that is 6, that is, and we say the best is where we have an aryl alkyl. Again, agonist activity increases. So let us understand when it is 1 to 2 carbon atoms, we have agonist activity. 3 to 5 carbon atoms, we introduce antagonist activity. Above 5, 5 to 10, again, we reintroduce. Please close. On the laptop screen. Please, I'm teaching. No. Please. So 5 to 10, again, especially when it's aryl alkyl, you introduce agonist activity. And I'm going to discuss that in a while, how that happens. Bang. Okay. Children. So I think I can even show you. Thought I had put that. This is my notes. I didn't put that anyway. I will show you on the receptor what happens. I'm sorry. I thought I put that. I thought I put the receptor, but it looks like I didn't. But I will show you, believe it, next time. Sorry, I thought I put that slide. So we have now looked at what happens when we change the terminal nitrogen. I'm sorry, I'll show you, maybe it's next time, how it is interacting with the different portions of the receptor, so that you will appreciate better. Then now we are also saying that is not the only change. So we have looked at ring A, we have looked at ring A, we have looked at ring B, we have looked at ring C, we have looked at ring D in terms of the terminal nitrogen, we have looked at ring E. 1 minute, I think. Sorry, I had a delivery person. So I was only summarizing that we have actually looked at quite a number of the peripheral changes. We started with ring A, we discussed ring A, we went to ring B, we went to ring C, we went to ring D, that's where we considered the terminal nitrogen. And of course, we went to ring E, where we said if you open and this comes there, you decrease activity. But if you remove the ether oxygen, you get the morphinans, which have activity. And now, of course, we have talked about that group there. But those are not the only changes that you can do. It was also found that you could add another ring. You can see now we have 5 rings. It was found that you can add an extra ring to this structure so that it becomes hexacyclic and with retention of activity. So that's what we are going to do. And when you add another extra ring, we call it annihilation. Annihilation is when you add another ring. So we can note adding a 6th ring across carbon 6 Again, the numbering is still the same. That is 4, 5. This is position 6. This is position 14. So adding another ring across carbon 6 and 14 of the C ring of dihydromorphine. If you look at it, you can see we have removed the double bond at position 6, 7, 8. We have no double bond there. That is why I'm calling it dihydromorphine rather than morphine, because indeed it is a structure of dihydromorphine, and the dihydromorphine has slightly higher activity than morphine, yields the compound we call etophine, which is an extremely potent compound. So we are also saying, in addition to all those structure changes that we were found, it was also found that we could do annihilation. And the annihilation is on ring C, where you can see we have added that 2 carbons and ethylene group. We have added an alkene group. We have added an alkene group there, and that alkene group gives us that ring there and that ring there. So actually, the total is now not 5 rings, but 6 rings. And when that was done, of course, with appropriate, remember always, with appropriate other structural changes, the resultant compounds were also found to be active. Kindly note that on the nitrogen, we have a terminal methyl group retained as in morphine. But if you look at that structure carefully, you also see that the group at position number 6 has also been changed. And the group at position number 6 is a methoxy group. And we already know adding a methoxy group at position number 6 further increases activity, because it increases the lipid solubility. So that increases activity. And then in addition, it was also found that position number 7 can also be changed, because you also want to have a balance on the water solubility and also increase the lipid solubility. So you can see this is 1, 2, 3. So we can say that is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. So it's 1, in fact, it's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we are adding this group there, which is 1, 2, 3, 4, 5 carbon atoms. So we are adding a hydroxybutyl group, because at this position, there is also a hydroxy group. The hydroxy group there is important, and you can see it's a beta hydroxy group to maintain, at least make sure you don't totally compromise on the water solubility. So it was found, so we are therefore, whenever we say a structural modification, yes, there is annihilation by adding the group we have added here in the middle. But it was also necessary to do a little bit more of structural modification, because the added structure was also able to interact with another allosteric center within the receptor to improve on the activity. So that gave us, remember we talked about what did we call them? I'm forgetting. Those I remember we did mention that even buprenorphine. Remember, we did mention buprenorphine, and when we look at buprenorphine, we'll also see that it's also an annihilated dihydromorphine, but the group there changes. So we are therefore saying that the changes that we bring in is not just periphery. We can also do annihilation of ring C and appropriate changes, and we get these compounds, the name I had forgotten is orepavine. We get the orepavine derivatives with increase in activity. Other structural changes in etophine include methoxy group at position number 6 and a butyl hydroxy group at position number 7, as I have discussed. Etophine has a higher lipid solubility. You can see that group there. All of us can appreciate that group there. We can appreciate the methyl group there. So it has a higher lipid solubility and opioid binding affinity than morphine. In fact, etophine is said to be almost 1,000 times more potent than morphine. Indeed, it is used in huge animals. You cannot use it in human beings. You use it in very, very huge animals. The replacement of the N-methyl group of etophine with a methyl cyclopropyl. So you can see this is a methyl group there. So we are saying if we replace that with a cyclopropyl, already we have the CH2. Already we have this as the CH2 there. And then now we put the cyclopropyl That is what we have in our trexon. So the minute we again replace the N-methyl group of etophine with a methyl cyclopropyl group, we use compounds with mixed agonist, antagonist, or partial agonist activity, and that is how we get buprenorphine. Buprenorphine is when this group here is changed from a methyl in etophine to a cyclopropyl group, and then also this group changes a little bit. It is made a tert butyl for better or increase in lipid solubility. But I hope we are appreciating the changes and the fact that when you do a certain change, it is affecting especially the lipid solubility. It is affecting the binding, and of course, occasionally it introduces, as we have said, the steric hydrons to bind a very important site within the receptor and therefore introduce antagonistic activity. So all that, I think we are repeating the same just to make it more clear. A partial opiate, that is buprenorphine, is a partial opiate agonist at mu receptors. Remember we said at low doses, it is very potent. It has very high affinity for the mu receptor and also good intrinsic activity. But as you increase the doses, it seems to get antagonist activity, and it gets to a point where we have ceiling effect, that further increase in dosage in the dosage of the buprenorphine does not have an increase in especially the euphoria or the respiratory depression. That's why we call it a partial agonist, because it will excite the receptors to a certain extent and then stop exciting them. And therefore, it looks like on the mu receptor, it has both agonist and antagonist activity, but it also has antagonist activity and the kappa receptors. As an agonist, it is 25 to 50 times more potent. Remember, when potency and efficacy, as you do in pharmacology, are two different things. Potency is the amount of drug in weight, the weight of that drug you use to elicit or to bring a certain activity. So we are saying buprenorphine is more potent. Indeed, it is more potent than morphine, but it is not as efficacious as morphine, because in some of the functions, especially respiratory depression and euphoria, it could be as potent, as efficacious in terms of analgesic activity, but when it comes to euphoria, when it comes to respiratory depression, it is not as efficacious, and therefore it is less toxic. When you compare buprenorphine with morphine in terms of toxicity, buprenorphine is safer. Even at very high doses, it will not kill because it does not cause fatal respiratory depression. It also is not as euphoric as morphine, but in terms of analgesic activity, it gives quite good activity. So kindly note, those are the differences between buprenorphine, which is considered to be a partial agonist. It has activity on the mu receptor, whereby it starts with very strong agonist activity, and it actually gets to a plateau, it gets to a ceiling. Increasing dose does not increase agonist activity, and it also has an antagonist activity at the kappa receptor. Etophine is approximately 1,000 times as potent as morphine, and arguably it is too potent to be released for human therapy. It is currently used as a tranquilizer for large animals. Like if you're talking about elephants, you want to transport them from one game reserve to another, you can use this as a tranquilizer and it will work. Yeah. Tell the other boys, yeah, it is live.
Can students face on the laptop?
Yes, please. No, it's not there. Please go.
Okay.
Sorry, I got one of my grandsons who is very inquisitive. He's even asking whether your faces are on the laptop, but he's young. He's just inquisitive. So this is just I've even illustrated here when we talk about potency and efficacy. So you can see when we have this is showing that this drug, this could be buprenorphine, very potent, because you can see you need to use a very low dose. If you're eliciting this kind of, that, let's say you draw that line there. So for you to get that activity with second drug B, you can see the dose, log drug dose. You can see the dose you require. When you look at this other drug A, which is highly potent, you can see the dose you require. And therefore, we can say A is more potent than B. But now when or opioid poisoning, and it will replace the full agonists, and it will sit on the receptor. It has lesser euphoria, it has lesser respiratory depression. For some of the patients, it can precipitate a bit of withdrawal symptoms, but it will be safer than the other opioids. So buprenorphine is a partial agonist at the mu opioid receptor, an antagonist at the kappa receptor. We've already mentioned that. It has very high affinity and low intrinsic activity at the mu receptor, and will displace morphine, methadone, and other opioids or full agonists from the receptor. Partial agonist opioids activate the opioid receptors in the brain, but to a much lesser degree than the full agonists. Example, of course, of full agonists, we already have discussed them, and I believe you already know them. The oxycodones, the oxymorphones, all of those are full agonists. Buprenorphine, an opioid used to treat opioid use disorder, as I have mentioned, because it has very high affinity for the opioid receptors. It can displace the full agonist, but it will not give this person full euphoria. It will also take charge. It will not also bring about respiratory failure, and therefore including addiction, acute pain, and chronic pain. When taken at the correct dose, buprenorphine prevents withdrawal symptoms and reduces drug cravings without causing the person to feel high or euphoric or sleepy, because we have said it is less euphoric compared. It's a partial agonist when it comes to euphoria. Buprenorphine lowers the harms associated with opioid misuse and gives people who are addicted to opioids a chance to stabilize their lives. It has a long half-life. Its respiratory depressant activity reaches a ceiling, as I've said, or a plateau. It has a moderate abuse potential, not as serious as that of morphine and the oxycodones and the oxymorphones. Because of its high affinity and slow dissociation from opiate receptors, larger doses of antagonists such as naloxone are required to produce a reversal. In other words, when it binds the receptors, it has very high affinity. It has very slow dissociation. So if you want to bring about or to give an antagonist, you must use very high doses of antagonist so that they can be able to replace it from the receptor. So that is buprenorphine. It has been used, and even I don't know whether you came across it again. I mean, no, you people have not gone for your attachment. When you go for your attachment, be checking out for these drugs. Check whether you find in like Madare, those ones who have the honor of going to Madare, check whether they have buprenorphine, check whether they have methadone, because those are some of the drugs that are used for people who are addicts to help them with the withdrawal symptoms. So these are the unrelated compounds we've already discussed. You can see etomorphine. You can see what the major difference there. This is buprenorphine. I hope you appreciate the difference there. It has a cyclopropyl that has a methyl. And again, when you look at this group here, it has similarities, but you can see this 1, 2, 3, 4, 5, a butyl group, as we have already said, an aliphatic butyl non-branched. But when you come to buprenorphine, again, it is 1, 2, 3, 4, 5, 6. So the length of the acyl group has been increased, and the branching has also been increased. So that increases the lipid solubility. So the buprenorphine, by increasing that also, it is taking care of increasing lipid solubility and therefore able for that compound to be able to bind, to pass through the membranes and bind the receptors. So that is the difference in structure, but this makes all the difference. It is the group that is at position number 17 that determines whether compound is it a mixed agonist antagonist. So the minute you change that from methyl group for that compound, it gets antagonist activity. When it's a methyl group, again that compound will have pure agonist activity. Sorry again, bear with me today. So I think we are done there. I hope you can appreciate the difference between atropine, buprenorphine, and the fact that one is a very strong agonist and the other one is a partial agonist. That if you have these two structures, because of the structural features, you can be able to differentiate. You can be able to account for the difference in activity. Of course, this is the ethinyl group, where it has a double bond there, it has double bond there, and that is characteristic of the annihilation. That is a characteristic of both compounds. But you can see both of them also have the methoxy group there to increase the lipid solubility. They have also an alkyl group there to increase the lipid solubility. But in both of them, of course, you also have a hydroxyl group to add or to at least improve on the water solubility, so that the compound, if a compound has too much lipid solubility, as we have already discussed, there will be depotization. It will remain in the periphery. It will not get it will not cross the lipid membranes because of depotization. So annihilated compounds, SAR of annihilated compounds is the same as for the epoxy morphinans. The epoxy morphinans are the epoxy morphinans actually the morphines. There is no difference. Lin F introduces additional lipophilicity. So once you introduce this ring, you can see even that ring is lipophilic. So it introduces additional lipophilicity. Carbon 7 attachment can increase lipid water partition coefficient. We've already mentioned that. When the substituent position 7 is large enough, it interacts with site A and increases mu receptor affinity, especially if it is an aromatic ring, such as a phenyl ring. Although now we do not have a phenyl ring, but we have the butyl. That's a butyl group, and we can actually say it is. So usually, of course, when we name these compounds, we will not name it as a butyl. We look, and you have done that, I believe, in your naming. You must always remember that when we name, we look for the longest chain. So you'd have to go that way. So we cannot name it as butyl or something. We'd look for the longest chain and we'd go that way. And once we go that, we'd say that chain is 1 carbon, 2 carbons, 3 carbons, 4. So it is a butane. So 1, 2, 3, 4. So once we number position 1, we number position 2 there. So we would say 2, 2 dimethyl butane. I hope you have done UPAC, you have done nomenclature. So although I am calling this a butyl system, when we come to naming, we cannot name this as a butyl derivative. We must look for the longest chain, as we always do. So if we are going to say what the name, give the name of this chain, we'd say it's 1, 2, 3, 4, and then 1, position 2. So it is a 2, 2 dimethyl, 2, 2 dimethyl butane. So you can say it's a hydroxy, then you put a dash, then 2, 2 dash, 2 dash, 2, 2, another 2 dash, and then you say dimethyl butane. The way you normally, so you can be able to call that, of course, using the UPAC system. Remember, we always name using the UPAC system. If we look at this one, it is that. Remember, this should carry the lowest number possible. Even here, I hope we did so. 1, 2, 3. So I think we have to 1, 2, 3, whichever side. 1, if we number from this side, 1, 2, 3. So 1, 2, oh, sorry. If we number from this side, 1, let me remove that because can't see it clearly, because we must make sure that the hydroxyl group carries also the lowest number possible. If we number from this side, it carries carbon 1, carbon 2, carbon 3. So we cannot, if we number from this side, it carries 1, 2. The hydroxyl group carries, because it's the one which has priority. So we number from that side, that comes number 2. That comes in, always remember your UPAC system. That comes number 3, and that comes number 4. So the naming, therefore, indeed, it should be 2 hydroxy, because remember the hydroxyl group, or the functional group that takes first priority, has to have the lowest number possible. So this hydroxyl group must have the lowest number possible, which is position number 2. And indeed, all of them, actually, ultimately, all the groups should have the lowest number possible. Then that is 3, 3. So it is, I think we can number it as 1, 2, 1, position 1, position 2, position 3. So 1, so it's 1 hydroxyl, no, sorry, 2 hydroxyl, then 3, 3 dimethyl butane. So that's such that it helps us. So again, remember, go back to your UPAC system. You are the ones who have done organic chemistry the other day. So this is 1, 2, 3, 4. So again, position 1, position 2, position 3, position 4. So that is 2 hydroxy. 1, 2, 3, 4 butane. So remember when we name, but in case you are talking about the branching, you can be able to say that buprenorphine indeed does have a tert-butyl. It has tert-butyl side chain. That is correct. But when you come to talk about the whole chain, you must use a UPAC, a naming system. So what we are supposed to do, we give these 2 and then 3, 3. What we used to do is check the one which has the lowest. 2, 3, 3. Then, in fact, remember, you want to name it kabisa correctly. You would name this compound as an alcohol. If you want to do it completely the right way, remember, we should name it as an alcohol. Yes?
Yes, I'm asking about the naming.
I'm just saying,
can we name like 3, 3?
Allow me to correct it. I'm saying it's only that I wanted to show the hydroxyl group, but if you were to name it correctly, completely as a UPAC system, because this takes first priority, we would name this compound as an alcohol, right? So we would look for the longest chain that has the alcohol, which would mean we would go that way and we would go this way, all right? So this is carbon 1, that is carbon 2, and that's 1, carbon 2, carbon 3. So that is propanol. Isn't that correct? So indeed, that is if naming it. I was naming it as to show that it is a substituent, because again, it's very difficult to name the substituent. Is difficult to name it, to give it the UPAC name. But if you are to name this compound, and you are given that compound and you are to name it as a compound, you would actually name it as an alcohol, because the hydroxyl group takes first priority. So you'd name one, you'd look at carbon 1, carbon 2, carbon 3, and therefore it's a derivative of propanol. And then at position, so number 1, position 2, position 3. And then now, because the substituents should have the lowest, the substituent should have the lowest number possible. These are 2. So I think I will name it from, that is carbon 1. I need my substituents to have the lowest number possible, 2, position 3. Because now here I will say it is 2, 2, because you see these are 2 substituents. So I'll call it 2, 2, and then 3, because I have 2, 2, then 3. Trimethyl propanol, because it is 3 carbon atoms. If I were to name it the other way around, then if I call this, you see, number 1, I call this number 2, I call this number, so this will be number 1, number 2, number 3. So how would that be? See, this is number 1. If I call this, I have started from this side, I've called this number 1, number 2, number 3, 2, 2. If now I start from this side, that would be 1. So this will be 2 for the hydroxyl group. And then 1, 2. And then here, it will be 3, 3. 3, 3. 2, 5, 8. 2, 4, 7. So you always have to go for the one where the total, and you can do it on your own. Whenever we do the UPAC system, we make sure that the substituent, the substituents carry the lowest numbers possible. And when they carry the lowest numbers possible, then that is the best way of numbering. Because you see, like now, this one, we are going this way and we are going that way. So at position, when we start numbering from this side, this will be position 1, that will be position 2, that will be this carbon there, that will be position 1, that will be position 2, that will be position, am I doing it correct? Because we look for the alcohol that way. So it's position, but you see the carbon which is carrying the hydroxyl group is the same carbon which is carrying the methyl group. But the methyl group, remember, will be the substituent. So it is actually on carbon 1. So it will be carbon, let me say it again. So 1 there, 1 methyl, comma, and then position 1, position 2, then position 2, methyl, like that. Then now if you start this other side, it will go just number like that. So this will be position 1. Again, position 2 will have 1. Position 2 will have 2 methyl. I hope we are together. That's carbon. We are starting now here 1. Position 2 has 2 methyl, and then position 3 and 3 methyl. So this was, remember, it's 2, 2. So this is 4, and that is 3. That is 7. This is 1 methyl, 1, and then this is 2, 2. So this is 4, and that is 1, 5. So the one where, so this is a better way of naming, where we have 1 methyl. So you're starting from this side. I hope you have seen how we have come, and we have done this before, because we are saying we must make sure that the the substituents carry. So I'm seeing this is a better way of naming it, where this one carries number 1, this carbon carries number 2, that carries number 3. Yeah, this carbon here. Yeah, because that will carry number 1, that will carry number 2, that will carry number 3, and that will carry number 4. Either of these, doesn't matter, you carry number 4. Because that is what you give us when we name that compound now as a product of an alcohol. That is the one which you give us the substituents having the lowest number possible. But I went to do things which are not mine. What I was saying is that when we come and talk about it as a substituent, because we are not giving the name, we are looking at it as a substituent. That is why I was saying we can actually call it like, we can call it hydroxyl, that one being hydroxyl, and then that is, but we still have to do it hydroxyl, and then we look at, that is carbon 1, carbon 2, carbon 3. So we can say hydroxyl, then that one is methyl, and then dimethyl 1, 2, 3 propane. Because, I want this to be noted. That hydroxyl group is very important in this substituent. So I'm naming it as a substituent. I am not naming it as a compound. I'm trying to name it like the way you can say hydroxy methane. That's not the right way. Like when you're naming the substituents, you can bring out the compound, the substituent you want. Like here, the major one I want to come out is a hydroxyl group. So I am naming it hydroxyl and then looking at the alkane. So that's why I was not bothering to name it, to give it the correct name as per UPAC name, because I want to show that indeed that compound or that compound has a hydroxyl group. I think even if you remember which compound was this, when we were studying the, when we were looking at the beta lactams, and there is the monobactams. I'm getting, I'm forgetting how we remember. Even remember when we were learning the beta lactams, we talked about hydroxyethyl, hydroxymethyl, hydroxypropyl. That is not the correct UPAC system, but it's because we want to highlight this hydroxyl group that I would prefer, instead of us going to the complexity of looking for the UPAC name for this group, we just may name it as a derivative of hydroxy group, hydroxy, but then you look at this and now you say it is 1, 2, 3, it is propane, it is 2, 2, it is 1, 2, 1, 2, 3, it is 1 methyl, 2, 2 dimethyl hydroxy group. So that now it makes it a little bit simpler than doing propanol as bring it as a derivative of the alcohol. That's the only bit I wanted to raise. That sometimes you find that when we look at like this one, we can just say hydroxy 1, 2, 3, 4, and we can say it's hydroxy butyl group. So we are really not so concerned about the UPAC system. We call it a hydroxybutyl group, meaning that we are so interested in the hydroxy group, we want to mention also that hydroxy functional group, because we are not naming a standalone compound. We are naming a substituent. So that's why I thought it's better to call it hydroxy without us getting involved with the UPAC system. But whichever way I believe is okay. So what were you asking before I think I did that? There was somebody who wanted to, yes?
Yes, it was about the naming.
Yes.
But I just understood. When I was counting, I thought it was to be a butane derivative.
Yeah.
So I was counting it. The longest chain would be 4.
One carbon,
that is
2,
3, 4.
Butane,
the one which is going to give the least number would be 2, 2 dimethyl butan 3 all.
2, 2.
So I begin from the other side.
Yes,
yeah, we have,
you see that could be correct, but I'm saying now when you come to name it as a substituent, do you see now you can't name it like that?
Yes.
That's a compound, yeah? You get my point.
Yes, I do.
Yes, you can't name it like that when you come to name it as a substituent. It's better now to look at it as hydroxyl. Okay, you come up with you leave the hydroxyl name, and then now you add the other portion, right? So you add now, you call this hydroxyl, and then now you name this other compound the right way, and then at the end, if it's a butyl, remember, since it's a substituent, you must end with that. It's butyl. You not go butane. You say butyl because it's a substituent. Are we together? You have got it right. Hello? Hello? You have. Because it's a substituent, it's not the main compound. That is why we cannot go the fashion of saying butane one on. We must make sure the last name is like butyl, propyl, whatever, ethyl, because it's a substituent. It's a substituent which has to be joined with the main compound. If it was the actual main compound, then that naming would be okay. So that's the bit I wanted at least us to appreciate, that when we name the substituents, let's remember the name must indicate that it's a substituent. So we have looked at buprenorphine. Then we're asking ourselves, which is better, morphine analogs, better or worse? And we can note morphine has 3 polar groups, phenol, alcohol, and amine. The analogs have either lost the polar alcohol group or have it masked by an alkyl or acyl group. They therefore enter the brain more easily and accumulate in the receptor sites in greater concentration, hence the better analgesic activity. That's, again, it depends on what analog. Some of the analogs have the methyl group removed for the no. So indeed, whether the morphine analog is better or worse in terms of stronger analgesic activity is dependent on the structural modification. So we can say, although I have tabulated that, we can still say that whether the morphine analog, when we talk about it's better in terms of higher analgesic activity, but once it has higher analgesic activity, remember it has also higher toxicity. So its higher analgesic activity or higher toxicity will actually depend on which morphine analog it is, because there are morphine analogs that have substituents such that they have increased analgesic activity. There are morphine analogs like codeine, which actually has lower analgesic activity. So for this question, I would say whether morphine analogs better or worse, I would really say it is dependent on the specific structural modification. And then I give examples. I say, like, if you're looking at codeine, the methoxy group at position number 3 decreases activity. So if you have to compare it with morphine, it's worse in terms of analgesic activity, but it's better in terms of toxicity, addiction, and so on. When you look at another one, like activity that you get is dependent on the specific structural modification. So I can't say cannot really be generalized. We cannot generalize that the morphine analog will be better or worse. The morphine analogs, analgesic activity or toxicity will specifically depend on the actual structural modification. What modification have you done to get that analog? If you have done it such that the activity increases, remember, analgesic activity will increase, toxic activity will increase. Remember, when analgesic activity decreases, toxicity also decreases. So I think that question will be added, that it is dependent on the structural modification of the specific unit. So then we move on now to the morphinans. The morphinans are similar in structure to morphine analogs, but what do they lack? We know they lack E-ring found in the natural occurring opioids. They lack the epoxy ring. They lack the 6-hydroxyl group. They lack the 7-8 double bond. So when we look at the morphinans, they do not only lack the epoxy group, they lack the 6-hydroxyl group. If they lack the 6-hydroxyl group, as we had seen earlier, lack of 6-hydroxyl group increases the lipid solubility, increases the activity of these compounds. Lack the 7-8 double bond. What did we say? Saturation of the 7-8 double bond changes the boat conformer to the chair conformer, and in so doing, it increases the activity. So we can therefore say, when we look at the morphinans, the structural the structural manipulation is such that the molecules have much higher lipid solubility and therefore much higher analgesic activity, much higher toxicity than morphine. Their general structure is represented by levofanol. So you can see again, let us be reminded, the numbering doesn't change because what we remove, we have only removed this group here. That is the group we have removed. That is what we have cancelled. So everything else remains intact because we have only changed we have only removed the epoxy ring, nothing else. And when you look at levofanol is that compound that has a hydroxyl group at that position and has a methyl group at that position. We talk about the morphinans, we have put a hydrogen there. Levofanol has a methyl group at that position, and that is a prototype. Levofanol is a prototype. Numbering system of morphinans is the same as for morphine because we have said the group that we have changed is not the oxygen or the ether linkage does not carry a number. Compounds are synthetic and are obtained as racemates. So these are synthetic compounds. We had done that when we did our classification according to the according to the source. We did say the morphinans are totally synthetic. And then, of course, again, there is stereochemistry. The more potent isomer has an R configuration alpha to the nitrogen. That is carbon 9. Again, the same carbon 9. This is a carbon 9 that we said and it is alpha to the nitrogen. That is a carbon 9, just carrying again the R stereochemistry or the R configuration, just like morphine, to give us the necessary activity. So we are saying this group again can change to give us different activities. Morphinans, removal of the E ring increases lipid water partition coefficient. We are removing the ether oxygen, increasing lipid water partition coefficient. In general, the morphinans are more potent than the corresponding 4,5 epoxy morphinans. Remember, the 4,5 epoxy morphinans is the same as morphine and analogs. And we can explain why are they more potent. We have removed those groups that were decreasing lipid solubility, and therefore the compound is bound to have much higher lipid solubility. Either bridge does not interact with receptor, and therefore its removal does not affect mu receptor affinity. So that's again very important for us to note that it's almost of no use, doesn't interact with the receptor, you remove it. Indeed, removal increases activity. The laboratory isomer with R configuration alpha to the nitrogen on carbon 9 is known as levofanol. Levofanol has higher analgesic activity than morphine. And I hope if you are asked, explain why levofanol has higher analgesic activity than morphine, I believe all of us can be able to explain that. We are looking at levofanol. It has higher activity. Its higher activity is due to higher lipid water partition coefficient. Why? Removal of the 6-hydroxyl group, removal, saturation of the double bond. That increases lipid water partition coefficient. Loss of the either oxygen and carbon 6 either oxygen and also carbon 6 hydroxyl group. That increases lipid water partition coefficient and also gives this compound higher receptor binding. Remember, we did mention once you remove the hydroxyl group, you saturate position 7, 8, you get the chair conformer. It has higher ability to interact with the lipophilic center and therefore gives this compound higher receptor binding, higher lipid solubility, and definitely higher activity. And the advantages of a morphine include better oral bioavailability because of the higher lipid solubility, longer duration of action, they bind the receptor much more. Disadvantage, higher toxicities than morphine. The higher the analgesic activity, the higher the toxicity. Then we go to another compound which is very important. When you go out there, kindly look for dextromethorphan. Look for dextromethorphan. The dextro isomer of morphinan. Dextro at what position? Dextro at position number 9. So when you talk about dextro isomer of morphinan, it means position 9 does not carry the R configuration, it carries the S configuration. It gives us the dextroisomer, and that is what we call dextromethorphan. So dextromethorphan, again, you can see methyl ME there. It means also the hydroxyl group of levofanol has been changed to a methoxy group. So this is more closer to codeine than morphine. Dextroisomer of morphine is known as the dextrofan, when you just put the dextroisomer, and is devoid of analgesic activity and associated toxicity. So the dextrofan, when you put the dextroisomer, as we said, it is a levoisomers that have activity. This, even when you remove the ether linkage, the same applies. It is a potent antitussive. That is the dextrofan. Or methylation of dextrofan produce dextromethorphan, which has higher antitussive activity. Remember, we said addition of a methoxy group at position number 3 removes or reduces analgesic activity and introduces antitussive activity. So although dextrofan has antitussive activity, addition of a methoxy group at position 3, just like codeine, further increases the antitussive activity. And when you go out there and look at some of the cough syrups, you will see they have dextromethorphan. And you can see because of the dextro already has all those euphoric activities have been reduced because it's already the dextroisomer. Then the methyl at position number 3 has further reduced the abusive potential of that compound, but introduced the antitussive activity. Dextromethorphan is as potent as codeine as an antitussive without respiratory depression and associated side effects, because we are saying the structural modification, as we've already discussed, gives these compounds or makes them devoid of analgesic and detoxicity, as we already mentioned. So this is levomethorphan. Again, it's levomethorphan because of that methyl group. It was levofanol when it has a hydroxyl group. Levofanol when it has a hydroxyl group, and it is levomethorphan, methyl because of the methyl group there. So levomethorphan, and it can be metabolized by cyclic or the cytochrome P450 enzyme to the levofanol. When it's metabolized to levofanol, remember, it's just a removal of that, conversion of that to the hydroxyl group, as you can see that, and then glucuronidation. So that indeed is the metabolism of levomethorphan. And you can have the dextromethorphan. Now, the dextromethorphan is this carbon here carries the S configuration rather than the R configuration. Kindly note, that is the only difference that we are talking about. Now, when you talk about dextromethorphan, dextro tells us the configuration at position number 9. The methorphan or methyl tells us it has a methyl group in place of the hydroxyl group in levofanol. So kindly note those structural changes. Morphinans. A tartrate is a salt or ester of organic compound, tartaric acid, and like carboxylic acid. And I was just because of this, when I see something, I like making sure that you understand. So again, remember, they still have the terminal, this group here, and this nitrogen there is still basic, but this time you can see this is a carboxylic acid. So you can use an organic carboxylic acid. You can use an inorganic acid. So when you use for the morphinans like levofanol, butorphanol, you use the organic carboxylic acid, tartaric acid, and just to get your salt. And you have drawn for you. So this is what you put here, and the nitrogen will be protonated, and this now is what will be in the surrounding. So you can have levofanol, tartarate. Again, note, this is levofanol. This is where position number 3, you have a hydroxyl group, and of course, it has the R configuration at position number 9, and that is the structure there. We have R there is a hydrogen. R prime is also a hydrogen, and R prime prime, which is there, is a methyl group. Butorphanol is the same as it will be similar with the compound that we had mentioned before, butorphanol. So it has a hydrogen there. It has a hydroxyl group there. Same. And it has the cyclobutyl at that position. Cyclobutyl at that position, and that is butorphanol, again, tartarate. Then dextromethorphan, as we have mentioned, again, that will have a methyl group there. It will have a hydrogen at that position. It has a methyl group at that position. And of course, we are reminded that position number 9, this position number 9 will have the one next. Position number 9 will definitely have an S configuration for it to be dextromethorphan. And I hope, it's something we have to build very, 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 very slowly. Something we have to build very, very slowly. I hope you are building it with me. We have to build it very, very slowly so that we are together. So, can somebody remind me which compound? There's a compound I said very, very similar. How are we then? No, butorphanol. Can somebody remind me this compound? This structure, which we said is very similar to another compound we had discussed. Can somebody remind me which was that compound, which has very similar, which is a morphine analog, which has a very similar structure to this? Which compound was it? Can anybody remember? Can anybody remember this butorphanol tartrate? It's like which compound we had discussed before? Can you remember? Can you remember? Can you remember? Kindly, can you remember? Can you remember? Hey, so there is a structure we can discuss, butorphanol, which is very similar to this, but it is an analog of morphine. Butorphanol is an analog of the morphinan. There's a compound we discussed, and we said it is a mixed agonist antagonist. You can't remember? Can you remember? Can you hear me, class? Sometimes it's good also to do a bit of exercise. Can you hear me, class? Can you remember? There is a compound we discussed. Butorphanol is similar to which morphine analog? Because this is a morphinan analog. Now bufine. Why are you putting a question mark? Stanley Masai, why are you putting a question mark? Stanley. Stanley, why are you putting a question mark? Now bufine, is that correct? Sam Getao, yes, you are saying something? Anybody else? Buprenorphine, we have just discussed buprenorphine. Buprenorphine is anelated. And it's buprenorphine is an norepinephrine. It is anelated. It is a hexacyclic compound. This one is 1, 2, 3, 4. In fact, this has 5 a beta-cyclic. So it cannot be buprenorphine. We have just discussed buprenorphine. Buprenorphine has 6 structures. Getao, look at your structure. Anybody else? Any other suggestion? Yes. So Stanley, thank you. You are correct. Indeed, they actually have. You can say butorphanol is, of course, a morphinan. It is an analog, which is a synthetic of the morphinans. But indeed, when you look at nalbuphine has the same structures. It has a hydrogen hydroxyl group. It has this, but of course, the structure, the other rest of the structure is the 4,5-epoxymorphinan. So the nalbuphine is a structural analog of morphine. Butorphanol is a structural analog of the morphinans. Dextromethorphan, we've already discussed, and we have said is a very, very good antitussive. Structure activity relationships of the morphinan, we have said is very similar to that of the morphine, and that is good because it makes it even our work easier. Structure SAR is the same. The 3-hydroxyl group is optimal, and the 3-methoxy group, as we have seen in the dextromethorphan, is less active. The nitrogen substituent produces the same activity as in morphine. So when you put a large group at that position, you expect the same activity. When you put large groups, you introduce an antagonist activity. No other substituents may be added to the ring. As we have said, the C ring must be unsubstituted. As you have seen, we've removed the 6-hydroxyl group. We have even saturated the ring. Position 14 may be substituted with a beta-hydroxyl group with increase in analgesic activity. So we are therefore saying the SAR of the morphinans is the same as the SAR of the other compounds. So therefore, we can introduce groups here as we have done. Remember, we have done so when we were looking at the morphine and analogs, and when we introduced large groups here like naloxone, naltrexone, we made the compounds to be antagonists. We made the compounds to be antagonists, or we made some of them, like if you look at when we introduced in morphine, when we introduced this group, we got nalophine, and nalophine is a mixed agonist antagonist. So you're saying, so that when we put an allyl group, when you're looking at the morphinans and you put an allyl group there, then we have levalofan. So the compound is called levalofan from levofanols. When it is a methyl group, hydroxyl group, it's levofano. When you put an allyl group, it's a levalofan. Antagonist 5 times that of nalophine, and it has weak agonist activity. So you can still say it is a mixed agonist antagonist, but you can see it is a much stronger antagonist than nalophine. And we expect that because we have said there is change of structure. Then when we do this, we put this group there, we call it cyclophan. It's a narcotic antagonist, so very similar to naltrexone. Stronger agonist, stronger. So it's not a pure agonist also. It's a narcotic antagonist, stronger agonist than morphine, but it was found to be hallucinogenic. So it also had both. It's a narcotic antagonist. It also has strong agonist and morphine, but unfortunately, it was found to be hallucinogenic. So I think it was discontinued from the market. And then we have the one we had called butorphanol. And remember, very similar to nalbuphine, of course, with the exceptions that we have mentioned, hydroxyl group at that position, the cyclobutyl group at that position, and a beta hydroxyl group at that position. So butorphanol is a stronger agonist than morphine, and also a weak antagonist. So again, it has both, just as we expect of nalbuphine. It has low dependence liability. When it becomes partial, then when it gets agonist activity, then the dependence becomes a little bit less. Partial agonist and partial antagonist activity to the mu type opiate receptors, as well as partial agonist and antagonist activity at the kappa receptor. So the butorphanol is a little bit different as partial agonist and partial antagonist activity at both the mu and also the kappa opioid receptor. So that's butorphanol, but very close resemblance with what we had mentioned nalbuphine. So we can note the NRL derivative of levofano is what I've said is levalofan has higher mu receptor affinity compared to both morphine and naloxone. So levalofan, and we have reasons, and we have said because of this group, you can even see this, we have changed that there, and because of those groups, removal of the also a removal also of the group of the hydroxyl group which was there, then we expect it to have much higher activity. We can't be able to understand that statement from the structure. So the valofan much stronger than naloxone, and we can't be able to explain. You have saturated that, you have removed that group there, and therefore increased the lipid solubility of that compound. Not only increase the lipid solubility, by changing that boat conformation to chair conformation, you allow this group to have better interaction with the lipophilic center of that compound. That is the butorphanol. Butorphanol has higher mu receptor affinity, again compared to morphine. This is due to the 14-hydroxyl group and the following advantages: neutral dependence liabilities, as we have said, and it has limited respiratory depression. So it has something very close to what we talked about in buprenorphine. So it has something close to buprenorphine. It is a mixed partial agonist with agonist and antagonist activity. We've already mentioned that. It's susceptible to significant fast-pass metabolism and administered parenterally or intranasally. So we don't give it orally because it has very high fast-pass metabolism. Kappa agonists have lower ceiling analgesic effect and are not as effective as mu agonists in severe pain. Remember, we had said that when these drugs bind the mu receptor, that is when you get maximum analgesic activity. When they bind kappa receptors, they have lower ceiling analgesic effect and are not as effective as the mu receptors. That I think we had mentioned earlier. Metabolism of levomethorphan. This is our levomethorphan. Remember, levomethorphan will have position number 9. So our number 9 there. Position number 9, carbon. That carbon having the R for it to be level. If it is dextro, that will have the S configuration. It must have the methoxy group there. So for its metabolism, one of the things that can happen is just like codeine, cytochrome P450 enzymes, oxidative O demethylation to give us our hydroxyl group. And then once you get the hydroxyl group, it can undergo glucuronic conjugation and the compounds can be very rapidly removed from the body. So you can see we are starting from levomethorphan, a compound that has much lower analgesic activity, a compound, then we get to levofano, which is much more in analgesic activity because of removal of that compound there, because of removal of the methoxy group at that position. Again, I think we have discussed all that. So that is the morphinans, and I hope we have given quite a number of examples and indeed also shown that the structure activity relationship of the morphinans and that of the epoxy morphinans is actually the same. The numbering is also the same because the ether group that we have removed that is not part of the numbering. Is there any question up to there? Have you have any question? Question up to there? So we move on then to the benzomorphans. And remember, we said morphan is ring B. When we talk about the morphan, is ring B and B, the former ring, the former ring B and the former ring B and D. Former ring B and D, is that what we call the morphan? And then we put the benzo because of that. So you can see that is our ring A, which was the phenyl ring. Our ring B remains. We have removed the former ring C. So we have removed ring C. And now we have the former ring D is now a ring C. So we did mention ring now B and C here. And of course, this was B and D in morphine. So B and C is what we call the morphan. And then now we call the benzo, because we have the benzo ring. And now that we have removed a full ring, the C, which was in the morphine and analogs. Therefore, for this one, the numbering must completely change. The numbering completely changes, and indeed how it is numbered very differently. We start with ring A but ring A will give it the prime. So we start with this position 1. Here we call this 1 prime the hydroxyl group, which was position 3 in the 4,5 epoxymorphinans or the morphine analog. Now please note, becomes 2 prime. Kindly note that is very important, that this one becomes 2 prime, that becomes 3 prime, 4 prime. Remember in the other one, we are starting here 1, 2, 3. Now the phenyl ring, I repeat again, that carries the prime numbers, starting from the position next to the intersection of ring B and A, and that carries 1 prime. So indeed, we are starting there, and we are still going clockwise. The other one, we were going anti-clockwise. So we are still going clockwise, 1 prime, 2 prime, 3 prime, 4 prime. And we first avoid there. And then we go now to the Morphan ring. And now we number the Morphan ring. And we number the Morphan ring starting with the previous carbon 9. This was our previous carbon 9. So the previous carbon 9 in morphine and analogs, we give it position number 1. And now we go to the nitrogen, position 2, then position 3. So now, first of all, we number the piperidine ring, position 3, position 4, position 5 there. This is position 5. Now we go backwards. They like restricting us. So again, I say position 1, position 2, position 3, position 4. So we go to the piperidine, position 5. This is our former. That is our former position number 13. So that's our former position number 13. This is our former position number 14. So that becomes position 5. Now we go to ring B, position 6, position 7, position 8. And now our former position 14 becomes position number 9. So kindly note, it's very important that we note when we get the benzomorphans. They're not morphinans, they are morphans. The previous ones are the ones which were morphinans. The morphans, the benzomorphans, because we have removed a ring C, which was part of the numbering. The numbering changes, and it changes in a way that ring, the phenyl ring or the aromatic ring, carries the prime up to 4 prime, and then we start the numbering from the former position number 9. That is the carbon alpha to the nitrogen, and we are going anti-clockwise and go from 1 to 2 to 3 to 4, and then again 4, and then to 5. And let us remember the 5 is the previous 13. And then now we go back to this ring number, the rings B, 6, 7, 8, and then we go to a position 14, which carries number 9. So the maximum, the highest number in these compounds is position number 9. So very much importance is to remember that this is where, this position is where our ring C was. Like that. Compound was like that. So you can see this indeed, and this are vestiges. So those are groups. This is like if it was coming like that, then like that, like that, and like that. So if I remove this there, I can say this is now what is becoming R2. And then you remove that, you remove that, you remove that. So this is a vestige or a remainder of ring C. And this one here is a remainder of ring C. So the substituents that are found in position 5 and position number 9, that substituent there and that substituents there are vestiges or are what is remains, the remains of ring C, and they must be there for the benzomorphans to have activity. So you must have a substituent at position number 5. You must have a substituent at position number 9, considered to be the vestiges or the remains of the ring C. And they are very, very important, because when you have that small vestige there, then we still have our quaternary carbon, which is directly attached to our phenyl ring. So we still have the what we had mentioned as a requirement for analgesic activity. And then, of course, this was our position number 14. So kindly remember that those bases R1, in here we are calling it R2 and R3. It can be called anything. You can start here as R1, R2, R3. So here we have started R1, R2, R3. So remember, R's don't matter. Really don't matter. It all depends. If I call this R1, you consider it as R1. If I call it, it doesn't matter where I call R1 or R2. It's just for one's convenience. So, but what we are saying is that R3 and R2 and R3 must be present, and they should be small alkyl groups. Indeed, in most of the compounds, they are small methyl groups. They are usually methyl groups for these benzomorphans to have activity. As also, as we note, is that the stereochemistry or the orientation of R3 is very, very important for activity. It must carry a specific orientation, notably the alpha orientation, if this compound is going to have optimal activity. This can change. The orientation of the small group at position number 9 can be either alpha or beta, but depending on the orientation will have an influence on the amount of analgesic activity the compound will have. But of importance, what I want you first of all to note is the importance of the difference in the numbering. Kindly master that numbering. Master the fact that position 5, 9 must also have small alkyl substituents, and more often than not, they are actually small methyl groups. Benzomorphan's effects on binding the receptor on the 2' position and then substituent modification are the same as in morphine. In other words, now we have changed. In morphine, that was the 3' position and the N substituent. They are saying effects on binding the receptor on the 2' position and N substituent modification are the same as that of morphine. Then, unlike previous series, the dextroisomer retains analgesic activity, but the levoisomer is more potent. So we are saying, unlike the other ones, remember, like when we mentioned the dextrofan, we say the dextrofan is devoid of analgesic activity. But here we are saying even the dextroisomer retains some analgesic activity, but still the levoisomer is the one which has higher activity. The levoisomers have the R again configuration at carbon 1, which is alpha again. This is carbon 1, remember, is the one which was carbon number 9. So kindly remember, and this carbon 1 is carrying R for the levoisomers throughout, 9R, 1R, which is alpha to the nitrogen in morphine. In other words, the carbon 9. I've tried to make sure that I mention it that way so that you do not confuse. So we are saying, yes, in this numbering, it's carbon 1, but it is equivalent to carbon 9, or it corresponds to carbon 9. And although the dextroisomer has activity, the levoisomer has high activity, and it must carry the R configuration for maximum activity. R2 and R3 are essential for mu receptor affinity, and they must be retained. You remove them, and once you remove them, then you find that the activity changes. We have said, you can see this compound, although R1 and R2 and R3, kindly note, R2 is not allowing for any other change, and we will not get any compound with any other group at that position but a hydroxyl group. No other group. I don't think we have any other group at that position apart from hydroxyl group in the benzomorphans. I don't think we have any other group. Unlike the morphinans, I think all of them indeed have the hydroxyl group at that position. So when we look at the SAR, I hope you have noted the structure, the change in numbering, and the fact that the position 5NR must have the vestiges, and they're very important for activity. Structure-activity relationship of the benzomorphans follows the same pattern as the morphinans. The nitrogen substituent R3 follows the same rules as the morphinans and morphines. However, antagonist substituent produce analogs with a higher agonist-antagonist ratio. That's the only difference, that when you have the antagonist substituents, although they are supposed to be antagonists. The substituents, like where you have mixed agonist, antagonist, then you find for the benzomorphans, the agonist antagonist ratio is much higher. So even where you have mixed agonist, antagonist, agonist activity is much higher for the benzomorphans than the other compounds. R1 and R2, see now here have changed. Sorry, I should have retained the same. Sorry about that. So now I'm calling them R1 and R2. It's what we call them here. We're calling them R2 and R3. Let me see which structure I'm looking at. Yes, I think I'm looking at this one where you have R1 and R2. Let's see. Oh no, you know as we move on. But note, so we are calling them R1 and R2, and here we are calling them R2 and R3. So they are the same. That's why I said sometimes they're given different names. So here I'm calling them R1 and R2, yet in the other one they were R2 and R3. R1 and R2 substituent must be present to supply the vestiges of ring C. They must be there. And R1 and R2, again, the other one, you have called them R2 and R3, are usually methyl or a similar lower alkyl group. But to be honest, I don't think I've seen any other group. In almost all of them, they are small alkyl groups. And we are saying R2 must be alpha down, since the benzene is beta up. For the analog to have agonist activity, R1 can be alpha down or cis. Now here we need to get which is R1. So here, this is R1 and this is R2. So we are therefore saying R1, R2 must be alpha. Yes, just as I told you before, it's good for us to make sure. I'm sorry that I changed the naming. This is the R2. This group here, the one at position number 5, must always have the alpha orientation. This can have alpha or it can have beta. So the R2 has always to have the alpha orientation for the compounds to have optimal analgesic activity. However, this one, in fact, we can call them R5, must always have the alpha orientation. R9 can have the alpha or beta orientation, but the beta orientation will have much more analgesic activity and toxicity than the alpha orientation. So R1 and R2 are usually methyl or similar low alkyl groups. I hope I've corrected that. You can see it in your mind. R2 must be alpha. Let us, for simplicity, say the R5, meaning it is a group at position number 5 must be alpha facing down. Since the benzene is up in terms when you draw the structure for the analog to have agonist activity. R, let's call this as the 9. R9 can be alpha down, which we call cis, or even this one is cis, producing analogs with activity about equal to morphine when it is alpha, or it can face up, which we call the trans, producing 4 to 30 times as active as morphine. So all we are saying here, it's important to note that the group, the methyl group or the alkyl group at position 9 can change. It can either carry the alpha orientation or it can carry the beta orientation. And we are saying the beta is the up, the alpha is the one facing down. And when it faces the alpha, when it is facing the down, is what we call the cis. And when it is facing up, we call it a trans. And this one, when it carries a trans orientation at position number 9, the compound has 4 to 30 times as active as morphine. But the same way, it will have the same addiction, it will have the same toxicity. When it is carrying the alpha orientation or facing down, then it will be equipotent with morphine. The beta agent will support narcotic addiction, while the alpha series will not. Alpha must be R4 must be hydroxyl group or methoxyl group, but I don't think I have any compound where I have it as a methoxyl group. So that is very important for us to note that indeed here the orientation of these groups is also very, very important. The orientation of those groups is also very, very important, whereby we are saying this position number 5, which we are calling R1, must always have the alpha orientation for the compound to have activity. Whereas this one here can either carry the alpha orientation or the beta orientation, and the orientation of R2 will determine the amount of agonist or agonist activity, and therefore also the toxicity. Alpha isomers are superimposable on morphine, but have a higher mu affinity than morphine. And we can say, therefore, in conclusion, beta isomers have higher analgesic activity than morphine, than the alpha ones, which have slightly or are almost equipotent with morphine. The alpha and beta isomers also have high lipid water partition coefficient compared to morphine. If you look at them, you remove the hydroxyl group, you have moved the ether linkage. Although you have removed the beta link, seems like they still have higher lipid water partition coefficient compared to morphine, which further increases their analgesic activity. The weak alpha isomer are preferred clinically due to their lower dependence liabilities. Remember again, as we had earlier discussed, the higher the analgesic activity, unfortunately, the higher the toxicity. So although the beta isomers, which are facing up, all trans at position number 9, are more active in terms of analgesic activity, they will also have more toxicity. And because of the more toxicity, they will have more addiction liability. So you find clinically it is the alpha isomers, where the methyl group or the alkyl group is facing the methyl group at position number 9 still is facing down or is cis. That is what is preferred. And now we give the examples. The examples, pentazosine. And if you look at this, is pentazosine, and you can see from the name penta, means there's somewhere where we have a 5-membered group, and indeed the R group there is a huge group, 1, 2, 3, 4, 5, but there is branching. There's branching there, and R1 is a methyl group. We'd already said this one is usually also a methyl group. So you can see that is a big group there, and I think that one is also a mixed agonist-antagonist, or phenazosine. Now, phenazosine again is having this group very big, CH2, CH2, C6, H5. Remember where we said, like in ethyl, phenyl, morphine, and we say the minute you make this group beyond 5 carbon atoms, the compound becomes an agonist. So that should be an agonist. Cyclazosine, again, cyclazosine should approach antagonist activity, but you see, we have said these compounds have slight difference there. They have a higher agonist antagonist ratio, and of course also we have metazosine. So we have metazosine, that is a structure. Look at that methyl group and a methyl group there. Phenazosine is where we have said that group is huge, and we expect that compound to have agonist activity. You have pentazosine, definitely this will have some antagonist activity. You have ketazosine. Ketazosine is a little bit different because in this position there, you have changed and you have put a ketone, so you call it ketazosine. And cyclazosine is again cyclo, when you put that. You can see, as I said, most of these groups here are actually small methyl groups for maximum activity. The metazosine, this metazosine is a prototype where you have those small groups, all the groups are methyl groups. That is a prototype. Metazosine is a prototype with a higher lipid water partition coefficient than morphine. Cyclazosine, methyl cyclopropyl, is a potent mixed agonist, antagonist. Remember, we did mention that these compounds, like when we looked at the other compounds, although they had a hydroxyl group at this position. We did mention for the others, when we put that group there, they became pure antagonists. Remember? They became pure antagonists when we put that group there. Or like when you look at nalofine and the other, now bufine, they became mixed. They became, when you didn't change, we didn't put a hydroxyl group at position number 14, they actually became mixed agonist, antagonist. So we are saying almost the same. Cyclazosine, which has a methyl cyclopropyl, is a potent mixed agonist, antagonist. But remember, we have said in this class of compound, the agonist ratio, they are have higher agonist activity than antagonist activity. It has a high lipid water partition and high incidence again of hallucinations, just as we said of cyclophan. Remember the morphinan, where we have the cyclopropyl group, we call it cyclophan, and we did say it also was found to have hallucinations. Of course, when it develops hallucination, the compound is just withdrawn. Phenazosine, a mu agonist, again, remember, because it has the phenethyl group, as I have mentioned, is an agonist, is more potent than morphine due to. So when we look at phenyl ethylphenazosine, we will compare it, as I have said, with ethyl phenyl morphine. Ethyl phenyl morphine is the one we compare with phenazosine. And remember we said when the group at position number 17, I want to continue repeating, has 5 to 10 carbon atoms, the molecule again changes from antagonist to agonist activity. This again is cutting across these compounds, and you can see in the benzomorphins we have the same here. Phenazosine, a mu agonist, is more potent than morphine due to a phenyl ethyl group that interacts with a site we are going to call site A. I'm going to show you that site, and also increased lipophilicity. Ketazosine has high affinity for kappa receptor. It has a slightly, as we have seen, it has a slightly different structure. Let us look at the number of that position, where it has position 8, because at position 8, ketazosine has at position 8 ketazosine, because that was at position 8, ketazosine has a carbonyl group. That's not something we have seen in the other structures. That is a deviation. But we have mentioned ketazosine has high affinity for kappa receptors, could be because of change of the structure. It's not common. Pentazosine is a synthetic opioid that has both partial agonist and antagonist activity, and is similar to butorphanol. Remember, we just discussed butorphanol. But when you look at pentazosine, of course, pentazosine does not have a cyclo. It does not have an alicyclic ring. Pentazosine has the aliphatic ring, aliphatic chain. If you look at pentazosine, it has an aliphatic chain, it has a double bond, and it has branching. So we are saying pentazosine is a mixed agonist, antagonist, very close to butorphanol, which we also said of the earlier compound. It's a synthetic opioid that has both partial agonist and antagonist, and is similar to butorphanol. Pentazosine has weak antagonist or partial agonist activity at mu opioid receptors with full agonist activity at the kappa receptor. Sometimes, of course, I don't expect you to completely remember all this, because it can be a bit too detailed. But we are saying it is a partial. It's important to note it's a weak antagonist, it's a partial agonist, and a weak antagonist. And indeed, it's a benzomorphin. That again finishes the benzomorphins, and we are saying that little exception where we have said that when we put antagonist groups, or groups that should give antagonist activity, we get a higher ratio of agonist to antagonist activity. So I have not seen we do not really have a pure antagonist from these compounds, and I also didn't see any pure antagonist also from the morphinans. But we are saying these compounds have that slight difference that they have higher agonist antagonist ratio, but the SAR sincerely is the same as what we have discussed earlier. Any question? Any question up to there? Naswali. Let me see whether I can get that that receptor so that before you go, you have an idea. Yes, here it is. So when we talk about the opioid receptor, then go up. This is what we are talking about. So you can see this compound here as the opioid. This is what we are talking about. And you can see this is a phenyl ring, which we have been saying must be there to interact with the receptor. And you can see it is interacting with this portion, D portion. And that D portion of the receptor is hydrophobic because this is hydrophobic to interact with that D portion that is found within the receptor, and that portion is also hydrophobic. So you can see that direct interaction of the phenyl ring, and that is why all these compounds, all of them all these compounds, all of them require that phenyl ring. Then you can see this other area here, this second area here, and this usually is for ring B and C. Well, this we are looking at these four compounds. That this is the ring E. I believe this is ring B. This is ring C, and this is ring E here. So A, B, then C, then where is our, here is our, and then here, if you look at it closely here, we're going this way. One there is our D. So that's our D. So this is our A, this is our B, this is our C. You can see the C there, with this double bond there, C, and that is our D, and that is our E. So indeed, it's only that they have drawn it D-dimensionally. So we can say that now that is the phenyl ring interacting with the complementary area within the receptor, and that area, we call it the D site. And that site takes up the aromatic phenyl ring. Then we have another portion here, which is a C, and that C, you can see it is taking this C, this one is taking that. This C is supposed to take B, ring B and ring C. This portion is supposed to be for ring B and C. So this portion at the inside there should also be hydrophobic. So that portion there should also be hydrophobic. And then you can see our ring, our nitrogen. This nitrogen here, remember, that one is ionic. It is polar. It is protonated as physiological pH. So it has its area C, and that area C must definitely be an ionic. It must have, because this is protonated, and you can see this interacts with that area, which is protonated area, and therefore it must be anionic because this area is cationic. And that is the area we are saying, this area, very, very important. And that is the area which is known. When this group is very huge, it is not able to interact with that position. Then I have talked about when you have a substituent, like when we talked about compounds like the orepavines, when we talked about etophine, like this could be the structure of etophine. I did mention that when that group at position 7 is very large, and the same applies even when this group here is very large, like when we have a phenyl ethyl group. So when this group at position 7, and you can see this is demonstrated here very clearly, this is position 7. When that group, and this indeed is a structure of etophine, remember it had a CH3, OH, and then it went like that. You know, this is a structure of etophine. So we said when that group is very large, or it could be even another group, because this is not etophine, because this one they have given it a phenyl group at the end, but etophine had CH2, CH3. Remember us saying, especially if the group that has joined at this position, especially if it has a phenyl group, it can very well interact. This one, we call it the allosteric, an allosteric site within the receptor, an allosteric site A. So even when this group here is very large, like when we are talking about phenyl, CH2, CH2, and then a phenyl group. Like that. So even when we have a very large group at position number 17, like we have talked about phenazozine, as we have talked about ethyl, phenyl, morphine. This large group at either position number 17 or that large group at position number 7, they allow that molecule to have other interactions that other molecules with small groups are not able to undergo. When you have a big group, I repeat again, at position number 7, especially when it has a phenyl group and also a big group at position number 17, again, especially if it's an aryl group, it allows that molecule also to interact with another area, which we call an allosteric site A. And when it interacts with that allosteric A, then that is how the activity of this compound is changing from antagonist activity to agonist activity. So that explains why phenazozine is an agonist, because phenazozine has a very big group here. That explains why ethyl, phenyl, morphine is an agonist, because it has a very big group here, which allows it to interact with this allosteric site A. And interacting with this allosteric site A, it changes from antagonist to agonist activity. So I hope, I thought it's I thought I had wanted to import this or export it, I think, to get it from here and export it up there, but unfortunately I didn't. But that is exactly the explanation. Why phenazozine? Why ethyl, phenyl, morphine? Although the groups at position number 17 are between 5 and 10 carbon atoms, those compounds have agonist activity rather than antagonist activity, because they are able to interact with an allosteric site A, which is found within the opioid receptor, and therefore give you agonist activity. So the site within the receptor, for purposes of lack of confusion, where the benzene ring, the phenyl ring carries A, where whatever site it interacts with carries D, so that you do not confuse. So that is A and that is D, and this the allosteric site within the receptor is what is called A. The anionic site is called B. The hydrophobic site, which accommodates ring B and C, is called C. And the hydrophobic area, which accommodates a phenyl ring, is called D. So kindly note the difference, or the fact that they are named in an opposite manner. The site is called D. The lipophilic hydrophobic area is called D, interacting with site A. The other one called C, so you go from D to A, whereas the other one you go from A to B. From A, sorry, actually you go from A to E. So that helps us not to confuse. So is there any question? So the compounds have, sometimes these things you do them along, it's quite some time. The compounds I was thinking about, where we talked about hydroxy ethyl. You remember the carbapenems. You remember the carbapenems? And that group at the group that we had at position number 6, which had the alpha orientation, and that group was the one responsible for very strong beta-lactam stability. And instead of now naming it using the UPAC system, we call it hydroxyethyl. Because when we call it hydroxy, we are now able to say the ethyl. We don't call it ethane, we call it ethyl, because it's a substituent. And that is why I was saying, even for these other substituents, we can easily call them hydroxy and then look at the alkyl and then make sure we add with ly. So that any substitute, the E in the parent compound carrying YL, any substituent, if it's an alkyl substituent, so that is why, and repeat again, instead of using the UPAC naming system, We use a simple naming system where we mention the hydroxyl group and then we look at the hydrocarbon section and see how we can name it so that it becomes a substituent, and we call it hydroxy something. It can still have the hydroxy 1122. That is not a problem. But then finally, we call it, if it has 4 as the longest, we call it butyl. So that we call it hydroxy. It can be 1 methyl 2, 2, whatever, butyl as a substituent that is in that position. Sometimes it's important to be able to give it that name so that by just looking at it, and you can be able to do that because you have actually, you can remember more of the pack naming more than me. You can be able to do that. That can give you, that especially when you come for orals or when you are an A student, that indeed does prove you really do understand. But when you can be able to go beyond what the other ordinary student does. So I think with that, you can be able to call it a day. The other class, I'm teaching you and also 5-1. Then we have managed to get an extra lesson because unfortunately, they have only added us 1 month. So we do need to have an extra lesson. So the other class, I will be giving them the extra lesson, I think on Friday. So you need also to look for time. We have an extra lesson so that we can finish as early. We have to finish, unfortunately. So if possible, I'll be overloaded because that means I'll be having, instead of 3 lessons a week, I'll be having 6 lessons. But since we are the ones to blame for the riot, for the strike, which really did not give us anything, then we have to sacrifice. Because an addition of 1 month in in January, I can't just finishing. So I think we kindly try and see whether you have any free time. And we can, and then I check with what I have or with my calendar. I see whether I can be able to have an extra class. Is Ian in this class? I'm looking for an Ian. I don't know whether Ian is in 4-1 or 5-1. All right. Is there any question? So I'll send you, as I've said, I think after this, I'll work on the assignment. I've already written the questions, only typing them. I'll work on the assignment so that you can do, the 2 groups can do a similar assignment. I think by next week, we should be able to finish the narcotic analgesics and perhaps also move on to antagonists. I'm hoping so. And then you can tell me when we should have a fast start. So is it after the first talk a bit broader? So with that, see you. Please make sure you give me an extra lesson. Otherwise, the other class will be ahead of me. And that will not be good.